Okay, so this is on what they call periodic functions and symmetry. This whole chapter is on graphing. Okay, we're going to go through graphing all 6 trig functions. By the time we get done, we're going to do it with and without a calculator. By the time we get done, you'll have to graph all 6 trig functions without the graphing calculator. And then when we start changing the equations, like when I say you have to graph the originals, you have to graph like y equals sine of x without a calculator, y equals cosine of x without a calculator. But as soon as I start changing the equation to like y equals 2 sine of pi over 4x plus 5, then we go to the calculator. Okay. But for this part, we're going to go back. This actually ties in a little bit with what you did in Algebra 2, okay, with symmetry, and we're going to talk about periodic functions. Number one, on the symmetry, like on this one, there's a parabola. This one is symmetric with respect to the x-axis. You could fold that graph over the x-axis. If we took and folded it along this line, we get the same graph. So that one's symmetric with respect to the x-axis. That's just the parabola y equals x squared. Remember, the way you tell it's a parabola is by the exponents. If it's a y to the first and an x squared, it's going to open up. If it's positive, if the number in front is positive, it's going to open up. If the number in front is negative, it's going to open down. If it's an x to the first and a y squared, positive number in front, it'll open to the right. Negative number in front opens to the left. Okay, so that one's symmetric with respect to the x-axis. Okay, if I give you something like this, if they give you part of a graph and say, I want that to be, oh, I said that wrong. That one's symmetric with respect to the y-axis. Did I say x every time? Gosh, darn it. Okay, symmetric with respect to the y-axis. Okay, on that one, you can fold it over the y-axis. On this one, if I give you the graph, if I give you this for a starting graph, okay, if I said I want that to be symmetric with respect to the x-axis, okay, then you basically count points and say, okay, I went up 1, 2, 3, 4, 5 points, so go down 1, 2, 3, 4, 5 points, okay, and then connect those so that it's symmetric. On this one, if I go up 3, go down 3, okay. On this one, I went up 2, 4, 6, 8, so go down 2, 4, 6, 8, okay. And this one, I went up 4, so you got to go down 4. It's got to be symmetrical. Okay, so you end up with a graph like that. And if you can fold it over the x-axis, okay, then it's symmetrical with respect to the x-axis. Okay, the other one was symmetrical with respect to the y. If they give you something like this, just part of a line, okay, array, a vector, okay, and they might say make that symmetric with respect to the y-axis. If you make it symmetric with respect to the y-axis, okay, then you got to count points, okay. If they said make it symmetric with respect to the x-axis, then it would be down here, okay? So that's a little bit of the symmetry. You ought to be able to fold it over an axis, okay? On this one, if I said make this symmetric with respect to the x-axis, okay, you would actually end up with a circle, okay? Now, you should be able to fold that over this half, fold over to the bottom, okay, and it's symmetric with respect to the x-axis. But this one has an interesting property that if it's a circle, you could fold this half over on top on the y-axis. So this one is actually symmetric. This one is symmetric with respect to, and the author is going to use WRT with respect to the x-axis, the y-axis, and the origin. Now the origin, if you can rotate your graph 180 degrees about the origin, like if I put a pin here and rotated my graph 180 degrees, I would get the same graph, and that's symmetric with respect to the origin. Okay? take another one. If I took this graph, okay, this is kind of like a cubic graph. If I took that graph, let's see if I can do it here. But if you put a pin here, rotate it 180 degrees, am I going to get the same graph? Yeah. Okay. You'd end up. Best way to show that maybe. If I start with this graph, if I put a pin here at 180 degrees, notice how it's shaped. If I rotate this graph 180 degrees, do I get the same graph? Yeah. And that's the easiest way you can tell on symmetry with respect to the origin is actually, if you have to, trace something on another sheet of paper, put it on top, and rotate it 180 degrees. So this one's symmetric with respect to the origin. Okay, this would be another one. This is like a y equals, this is one you should recognize from Algebra 2. Y equals x cubed. Same thing. If you put your point here, put a pin here, and rotate that, you would end up with exactly the same graph. So that one is symmetric with respect to the origin. Okay? Just do a little sketch. Symmetric with respect to the origin. And you can graph these on your graphing calculator. If you put y equals x to the third, it will graph it. Okay? On this one the author talks about the graph being periodic. Okay? If I told you this graph repeats every 1, 2, 3, 4, 5, oops, go back, hang on, let's go back. If I say it repeats every 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It repeats every 12. Okay? So it's at 0. This y value is 0 and it's going down. When is it at 0 and going down again? Right over here. So then you could go over 6. Okay? And down to here. Okay, and the graph repeats. And go up to 6. Okay, so this graph is periodic. It repeats every 12 units. You could also pick a point like up here, okay, to here. Say the graph is up at positive 5 and going down. When is it at 5 and going down again? Over here, and if you count spaces, it's also 12 units. It repeats every 12 units. Okay. Okay, on this one, if I give you a graph like this, it has an open circle here, solid point here. Okay, if I say it's an open circle at 0, and there's an open circle here, when does it repeat? This graph repeats every 2 units. Okay. So it's periodic every 2 units. And that would tell me if I wanted to continue the graph, okay, I could just repeat the graph. Okay? And we're going to do that with the 6 trig functions. Okay? Okay. Now, go down. Now, after looking at those graphs, now let's go through the notes. There's some special names. Okay? Okay, for symmetry. So if it's symmetric with respect to the y-axis, okay, the ones that you could fold it over the y-axis, like the first parabola, okay, that one has a special name, and that's called an even function. Okay, it's even. And if you look at the graph, the first one that we did, it was like this, the parabola. If you fold it over the y-axis, you get the same graph. in our y equals x squared, if our x value, let's look at two x values. If our x value is negative 2 squared, the y value up here would be 4. If x was 2, the y value would be 4. So, another way to say that, if the x values are opposites, the y values are the same. How they write that in algebra and in trig, if it's even, if the x values are opposites, the y values are the same. That's what this says. If you look inside, look at the x values. The x values are opposites, but look at the sign in front of the y. F of x is the same thing as y. The y values, if you look at this, the y values are the same. So even functions, you can fold them over the y-axis and get the same graph, okay, on both sides. Okay. Symmetric with respect to the x-axis. If you want to be famous in math, there is no name for that. Okay, it's just symmetric with respect to the x-axis. Okay. Symmetric with respect to the origin. And that's the one that you can rotate it. So you might want to put, you can rotate it 180 degrees about the origin and get the same graph. Right. And that one does have a special name. It's odd. And I just remember on that the O's go together. Okay, if it's even, it's symmetric with respect to the y-axis. If it's odd, it's symmetric with respect to the origin. Okay, an example of that one that we had was like y equals x cubed. If it looks like this, as an example, y equals x cubed. If you look at, let's say the x value 2, 2 cubed would be 8. So we'd be up here at 8. If you look at negative 2 cubed would be down here at negative 8. So on this one, if the x values are opposites, the y values are opposites. Okay? This way. So with the way they say that in the algebra form, okay, is a negative f of x equals f of negative x, or opposite of. Okay, so if you look at this, okay, look at the x values. X values are opposites. The y values are opposites. Okay, and that's the easiest way to remember that. Now, you can tell by looking at the graph if they're even, odd, or neither. Okay, by looking, is it symmetric with respect to the y? Can I fold it over the y? It's even. If I can rotate it 180 degrees about the origin, it's odd. But you can also do it without the graph and do it by the algebra. Okay, the author is going to have you do some of these. And the directions will just say determine whether each function is even, odd, or neither. Okay, an example. Say I give you f of x, remember that's the same as y, f of x equals x squared plus 1. What you have to do on every one of these is substitute in, everywhere you see an x, substitute in the opposite of x or negative x. So take your original, and everywhere you see an x, substitute in a negative x or opposite of x, and simplify it. If you take a negative x squared would still be positive x squared plus 1. And then what you have to do is you have to compare your y values. Okay, the x values were opposites. Are the y values the same, opposite, or neither? In this case, they are the same. So if you substitute in x values are opposites, y values are the same, okay, then this one is even. Okay? If the y values are the same, this one is even. So your final answer would be it's even. Say I give you f of x equals x cubed minus 2x. Okay, everywhere you see an x, you're going to substitute in a negative x. So you'd have a negative x cubed minus 2 times a negative x. So a negative cubed still be negative, right? And a negative times a negative would be a positive. Okay, now you have to compare these y values. Are they the same, opposite, or neither? They're totally opposites of each other, right? So these are opposite. Okay. If the y values are opposite, then it's odd. Okay. So you can tell by just substituting in everywhere you see an x. Another example. Say I give you f of x equals 4x plus 6. Everywhere you see an x, substitute in a negative x. Substitute in a negative x. And you get negative 4x plus 6. Are they the same y values? You got to compare y values. Are they the same, opposite, neither? That one's neither. Okay, it didn't change the x, the plus 6. So this one is neither. So this one is not even, not odd, it's neither. Okay? Okay, last example. Okay, everywhere you see an x, substitute in a negative x. Notice that exponent goes on the outside. And you're just to the fourth power or just the x. So negative to the fourth is positive. Okay, and then compare this y value with this y value. Same, opposite, or neither? Same. So this one is the same, so it is even. This one is even. That means this one would be symmetric with respect to the y-axis. Okay? Okay.